There is a moon in this solar system that is on fire. Not metaphorically, not in the way we describe a sunset or a red desert at dusk. On fire. Actively, continuously, violently on fire. Right now, as you listen to this, as you breathe, as the room around you sits quiet and still, its surface is painted yellow and orange and deep red, not by dust, not by oxidized iron the way Mars is red, but by sulfur. Sulfur compounds deposited fresh, constantly, by eruptions that have not stopped in the 4.5 billion years since this moon formed. It has no craters. None. A surface without a single preserved impact, because every crater that ever formed was buried almost immediately under lava and volcanic fallout. The entire face of this world is being repainted continuously from the inside out. The tallest mountain in the inner solar system, taller than anything on Earth, taller than Olympus Mons on Mars if you measure from base to summit along the local surface, sits on this moon. It is not a volcano, it is a compressional ridge, squeezed upward by forces that the moon cannot stop generating. It rises 18.2 kilometers above the surrounding plain. There is a lake of lava on this moon that is 200 kilometers across. Not a lake that occasionally fills, a permanent churning body of molten rock that has been observed to overturn its own crust in a slow clockwise wave, completing one circuit approximately every 540 days, predictable and relentless and measured. A single volcanic plume on this moon once deposited sulfur across an area the size of Alaska in a single eruption event. And no one knew any of this until 1979. The prediction that this moon should be volcanic, that it should be the most volcanically active body in the entire solar system, was published in a scientific journal 3 days before the first spacecraft ever reached it. 3 days. The paper was submitted before confirmation was possible. The spacecraft arrived, pointed its cameras, and the images came back showing exactly what the mathematics said should be there. The authors of that paper, Stanton Peele, Patrick Casson, Ray Reynolds, had calculated the interior of a world from gravitational equations alone. This is Io. It orbits Jupiter. It is not at peace. Tonight, you are going there. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in this story comes from real scientific research and observation. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Io was discovered on the 7th of January, 1610. Galileo Galilei was using a refracting telescope he had built himself, a 9-powered instrument, later improved to 20-powered, and he was observing Jupiter. He saw 3 small points of light arranged in a line near the planet. The following night, they had moved. By the 12th of January, he had identified a 4th point, and by the end of the month, he understood that these were not background stars. They were objects orbiting Jupiter. He called them the Medicean stars, after his patron. We call them the Galilean moons, Io, Europa, Ganymede, and Callisto. Io is the innermost of the 4. It orbits Jupiter at an average distance of 421,700 kilometers from the planet's center, closer than Earth's moon orbits Earth in terms of the ratio between moon distance and planet size. One complete orbit takes 1.769 Earth days. Not approximately, exactly 1.769 Earth days, to 3 decimal places, because this orbit is not drifting, it is locked. The lock is called the Laplace resonance, named for the French mathematician Pierre-Simon Laplace, who analyzed the orbital mechanics of the Galilean moons in the 18th century. The resonance works like this. For every single orbit that Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4 to 2 to 1. The ratio holds because the 3 moons exchange gravitational energy with each other at the same points in their orbits over and over again, and those repeated nudges prevent the resonance from breaking down. It is a self-stabilizing system. It has been stable for billions of years. The consequence of that stability is Io's interior. To understand what the Laplace resonance does to Io, you need to understand what a perfectly circular orbit would mean for a moon. In a perfectly circular orbit, a moon maintains a constant distance from its planet. The planet's gravitational pull is constant. The moon's shape is constant, stretched slightly toward the planet by tidal forces, but stretched by the same amount at every point in the orbit. There is no flexing. There is no change in shape. And because there is no change in shape, there is no friction generated inside the moon, and therefore no heat. Io does not have a perfectly circular orbit. The resonance with Europa and Ganymede continuously pulls Io's orbit into a slight ellipse, small but measurable, an eccentricity of approximately 0.0041. In absolute numbers, Io's distance from Jupiter varies by roughly 17,000 kilometers between its closest point and its farthest point in a single orbit. That variation in distance means the gravitational pull on Io changes as it moves, which means the tidal bulge, the elongation of the moon toward Jupiter, changes in height, which means the moon's surface moves. Every orbit, Io's surface rises and falls by as much as 100 meters under tidal flexing. Rock, not ocean. Rock flexing 100 meters up and down once every 1.769 days, because Jupiter's gravity is changing its grip. Rock that bends generates heat. The friction of material being repeatedly deformed transfers energy into thermal energy. In Io's case, the amount of heat generated this way is not modest. The total heat flow from Io's interior to its surface has been measured at approximately 100 terawatts, 100 trillion watts. For comparison, the total heat flow from Earth's interior, driven primarily by radioactive decay and residual formation heat, is approximately 47 terawatts. Io generates more than twice Earth's total internal heat output, and it does so entirely through the mechanical action of Jupiter's tidal forces. That heat has to go somewhere. In a world with a cold surface and a hot interior, heat migrates upward through whatever pathway is available. On Earth, that pathway includes slow convection in the mantle, geothermal venting on the ocean floor, and volcanism at tectonic boundaries. On Io, there are no tectonic plates. There is no ocean floor. There is one pathway, straight up through volcanic conduits, erupting onto the surface. The result is that Io's entire surface is volcanic. Not partly volcanic, not volcanically active in certain regions. Every square kilometer of Io's surface is either covered in volcanic deposits, actively erupting, or positioned above a heat source that will eventually produce eruption. Scientists have cataloged over 400 distinct volcanic features on Io using Voyager, Galileo, and ground-based observation data. Active eruptions have been observed at more than 150 separate locations. The number of eruptions occurring at any given moment, averaged across time, is estimated to be in the dozens. This is the world beneath you now, as you begin to approach. You are seeing it from distance first, a small sphere against the black, lit by the sun from one side, the other half falling into shadow. Even at this distance, the color is wrong. It is not the gray of Earth's moon, not the reddish ochre of Mars. It is yellow, bright, sulfurous, unnatural yellow, broken by patches of white and orange and a deep red-brown that sits near the equator, in a region you will come to know as the site of the largest persistent volcanic feature in the solar system. The yellow is sulfur dioxide frost. It coats vast portions of Io's surface, deposited by volcanic plumes that carry the compound high into the near vacuum above the surface, where it freezes and falls back down as a fine white to yellow powder. The deeper oranges and reds are allotropes of elemental sulfur, the same element but in different molecular arrangements that produce different colors depending on how rapidly the sulfur was cooled after deposition. Fast cooling produces red sulfur, slow cooling produces yellow. The surface of Io is a color map of its own thermal history. The surface temperature away from volcanic features is approximately -130 degrees Celsius on the sunlit side, dropping further on the night side. Step from the frozen sulfur plains toward any of the major calderas, and the temperature increases rapidly. Near the active lava lakes and eruption sites, surface temperatures exceed 1,600 degrees Celsius, hotter than the surface of some stars. These are not estimated values. They are measurements taken by infrared instruments aboard Galileo and Juno at close range, and by Earth-based telescopes monitoring Io's thermal output in the near-infrared band. The interior structure of Io, as modeled from gravitational data collected during Galileo flybys, consists of an iron or iron sulfide core approximately 900 kilometers in radius, surrounded by a silicate mantle. The mantle is not fully molten, but is pervasively partially molten, a global magma ocean, or something close to it, sitting in the upper mantle at depths of perhaps 50 kilometers below the surface. This layer is called the asthenosphere. On Earth, the asthenosphere is a zone of slightly softened rock that allows tectonic plates to slide over it. On Io, the equivalent zone is far hotter and far more mobile, and because Io has no plates, the magma simply pushes upward wherever the overlying crust is thinnest. The crust itself is approximately 30 to 50 kilometers thick in most areas, composed primarily of silicate rock, basalt and related materials similar to what you would find on Earth's ocean floors. But layered through it and coating it from above are deposits of sulfur and sulfur dioxide that give Io its characteristic appearance. There are no craters on Io. This statement needs to stay with you for a moment. Every solid body in the solar system that has been geologically quiet for long enough accumulates impact craters. The moon is covered in them. Mercury is covered in them. Mars has thousands, though erosion has softened many. Even Europa, despite its young icy surface, shows a small number. Craters are how planetary scientists read geological age. The more craters, the older and quieter the surface. Io has none, 0 preserved impact craters. Not because Io was never struck by asteroids or comets, it was statistically as often as any body in its orbital region, but because every crater that formed was buried almost immediately by volcanic resurfacing. The average rate at which new material is deposited across Io's surface, integrated across all volcanic activity, is estimated at between 1 and 10 centimeters per year. Over geological time, that rate has been sufficient to completely erase every trace of every impact the moon has ever received. Io's surface is, geologically speaking, extraordinarily young. The average age of material exposed at the surface is measured in thousands to millions of years, a geological instant in a solar system that is 4.56 billion years old. You are orbiting now, slowly. The surface below you is not still. Nowhere on this world is still. In the equatorial region, a dark structure sits within a vast plain of sulfur deposits. It is roughly circular, slightly irregular at the edges, and it is approximately 200 kilometers in diameter. This is Loki Patera. Patera is the term planetary geologists use for an irregular volcanic depression, not a simple circular caldera, but a collapsed surface feature with complex geometry. Loki Patera is not a vent, it is a lake of silicate magma, covered in places by a thin crust of cooled rock that is slowly, continuously overturning as the hotter magma beneath it circulates. Instruments have detected a thermal wave propagating around the perimeter of Loki Patera in a clockwise direction, completing one circuit approximately every 540 days. The wave represents fresh, hot lava being exposed as the crust overturns. The temperature of the exposed magma during these events exceeds 1,200 degrees Celsius. The lake, in its relatively cooler and more crusted phases, still radiates enough heat to be detectable by Earth-based infrared telescopes across 628 million kilometers of space. Further to the south, a different kind of volcanic structure marks the surface. This one does not look like a lake. It looks like a dark, irregular stain surrounded by a ring of sulfur dioxide frost that extends hundreds of kilometers in every direction. This is Pele. Pele is classified as a persistent volcanic plume, a vent through which volcanic gases and fine particles are continuously ejected upward at velocities sufficient to carry them 300 to 500 kilometers above the surface before they fall back down in a wide umbrella-shaped pattern. The material in Pele's plume is primarily sulfur and sulfur dioxide, but with a higher proportion of short-chain sulfur molecules, S2 disulfur, than most other Io plumes. The S2 is unstable and rapidly polymerizes after deposition, producing the distinctive dark red color of the Pele deposit ring. The ring itself is vast. The sulfur fallout from Pele's plume covers an area of approximately 1,200 kilometers in diameter, making it one of the largest single volcanic deposit structures identified on any body in the solar system. Pele's plume height, 300 kilometers, requires an ejection velocity at the vent of approximately 1 kilometer per second. For reference, the muzzle velocity of a rifle bullet is between 0.3 and 1 kilometer per second. The gas leaving Pele's vent does so with the velocity of a rifle shot, sustained continuously, directed upward into a near vacuum. Io's surface gravity is approximately 1.8 meters per second squared, about 18% of Earth's surface gravity. In that low gravity and thin atmosphere, Material ejected at 1 kilometer per second travels very far before it falls back. The plume expands outward in a perfect ballistic arc, tracing a hemispherical shell above the vent, the individual particles following trajectories that would be precisely predictable if you knew the ejection velocity and angle of each one. This is the moon that waited for human instruments to find it. This is where you are tonight. Prometheus is another structure on this surface worth holding in your mind. Unlike Pele, whose plume position and intensity vary, Prometheus has been erupting from the same location, or very nearly the same location, continuously since Voyager 1 first imaged it in 1979. When the Galileo spacecraft arrived 16 years later, Prometheus was still erupting. When New Horizons passed Jupiter in 2007, Prometheus was still erupting. Ground-based observers tracking Io's infrared signature in the following years confirmed it continued. The consistency of Prometheus is unusual even for Io. Its plume reaches approximately 100 kilometers in height, lower than Pele but persistent. The plume feeds a sulfur dioxide lava flow at the base that has been observed advancing slowly across the surface, moving the plume source slightly westward over time as the active vent migrates with the flow. The plume itself interacts with the advancing lava front, creating a system where fresh sulfur dioxide is sublimated from frozen surface deposits as the lava front approaches, then carried upward into the plume column above. This means Prometheus is not simply a vent, it is a dynamic system, a lava flow creating its own plume by vaporizing the ground in front of it as it advances. Beneath everything visible, beneath the sulfur plains and the lava lakes and the plume deposits and the dark calderas, the heat keeps moving. Tidal forces keep flexing the rock. The Laplace resonance holds its ratio. Europa completes 2 orbits for every 4 of Io's. Ganymede completes 1. The gravitational dance has not varied in billions of years and will not vary for billions more. The interior of Io is a furnace that cannot be turned off. You're passing over the Terminator now, the line between the sunlit hemisphere and the dark side. The sulfur plains catch the low angle of sunlight and glow a warmer orange than they appear at higher sun angles. The shadows of the mountainous ridges near the poles stretch long across the surface. The mountains of Io are among the strangest structures in planetary science. On Earth, most mountains are volcanic, built upward by eruption, or tectonic, pushed upward by the collision or subduction of crustal plates. Io has no tectonic plates, and its mountains are not volcanoes. They are compressional ridges, formed by a mechanism unique to Io, as volcanic resurfacing continuously deposits new material on top of old material. The cumulative weight compresses the lower layers. That compression generates horizontal stress in the crust, where the stress exceeds the strength of the rock. The crust buckles, and a ridge is thrust upward. Boosoli Montes, located near Io's equator, rises 18.2 kilometers above the surrounding surface. This is the tallest known mountain in the inner solar system. For comparison, Everest rises 8.849 kilometers above sea level. Olympus Mons on Mars, the largest volcano in the solar system, rises approximately 21 kilometers above the Martian datum, but has a base so wide that its height is distributed across a structure 600 kilometers across. Boisolar rises 18.2 kilometers from a relatively narrow base, making it one of the most structurally extreme mountains anywhere humans have imaged. The upper slopes of these mountains are cold, far below the caldera temperatures, above most of the sulfur dioxide atmosphere. The peaks of the tallest Ionian mountains exist in conditions not unlike deep space, cold, airless, irradiated by Jupiter's particle environment, lit by a sun that appears only 1/27th the angular size it appears from Earth. From the summit of Bossolomontes, Jupiter fills a significant arc of the sky. The planet's banded cloud structure is visible without magnification. The Great Red Spot, a storm system larger than Earth that has persisted for at least 350 years, rotates slowly into and out of view as Jupiter completes one rotation every 9.925 hours. The planet does not rise or set from Io's surface the way the sun and moon rise and set on Earth, because Io is tidally locked to Jupiter, the same face always pointing toward the planet. Jupiter hangs in a fixed position in the sky, never moving, while the stars wheel slowly around it. This tidal lock is the same mechanism that keeps Earth's moon always showing us the same face. The rotation period of the locked body becomes equal to its orbital period. Io rotates once on its axis in exactly 1.769 Earth days, the same time it takes to complete one orbit. The result is that if you stood on Io's Jupiter-facing hemisphere, Jupiter would be permanently overhead, drifting only slightly north and south as Io moves through its slightly elliptical orbit. If you stood on the opposite hemisphere, the side permanently facing away from Jupiter, you would never see Jupiter at all. The sky on that side is just stars and radiation, and the thin, barely there whisper of sulfur dioxide atmosphere pressing against your suit, sparse enough that the pressure would be measured not in atmospheres or bars, but in nanopascals, billionths of a pascal, roughly equivalent to the best vacuum chambers humans can construct in laboratories on Earth. The atmosphere of Io is, in the technical sense, barely an atmosphere. It is a surface-bounded exosphere, supplemented by volcanic outgassing. Its main component is sulfur dioxide, released continuously by volcanic venting and sublimation of SO2 frost deposits under sunlight. The total atmospheric pressure is between 0.3 and 3 nanopascals, varying based on volcanic activity, distance from the sun, and whether the surface frost is in sunlight or shadow. This atmosphere collapses every time Io passes into Jupiter's shadow. In eclipse, the surface temperature drops rapidly, the SO2 frost no longer sublimates, and the thin atmospheric column literally freezes out, precipitating onto the surface as frost. When Io exits eclipse and sunlight returns, the atmosphere regenerates from sublimation within hours. The atmosphere of Io is not a permanent feature. It is rebuilt from scratch, repeatedly, every time the moon passes through Jupiter's shadow, which it does once per orbit, for roughly 2 hours each time. You are still here. The surface below continues its slow, violent business. Somewhere beneath the sulfur frost of the sunlit plains, magma is moving. Somewhere near the dark stain of Pele, gas is rising at rifle-shot velocities upward. Loki Patera is overturning its crust, degree by slow degree, along its clockwise thermal wave. On the 7th of January, 1610, Galileo Galilei wrote down a small point of light near Jupiter. He did not know what he had found. Tonight, you are resting in the shadow of everything that point of light turned out to be. On the 5th of March, 1979, at 12:05 Universal Time, a spacecraft traveling at approximately 10 kilometers per second relative to the Sun made its closest approach to Jupiter. The spacecraft was Voyager 1. The distance at closest approach was 348,890 kilometers above Jupiter's cloud tops, less than the distance from Earth to our own moon. The encounter had been planned years in advance. Voyager 1 was part of a two-spacecraft mission launched in 1977 to take advantage of a rare alignment of the outer planets, an alignment that occurs once every 175 years that would allow a single trajectory to visit Jupiter, Saturn, Uranus, and Neptune in sequence, using the gravity of each planet to accelerate toward the next. The mission was called the Planetary Grand Tour. Both spacecraft launched in 1977, Voyager 2 first in August, Voyager 1 second in September, but on a faster trajectory that put it ahead. The instruments aboard Voyager 1 included a wide-angle camera, a narrow-angle camera, ultraviolet spectrometers, infrared radiometers, magnetometers, plasma detectors, and cosmic ray instruments. The imaging system was built around a Vidicon tube, a technology similar to early television cameras, capable of capturing images at resolutions that no ground-based telescope could approach for the moons of the outer planets. The images that came back during the Jupiter encounter were unlike anything planetary scientists had seen. Jupiter's atmosphere was resolved in extraordinary detail. The Great Red Spot showed internal structure, a rotating pattern of clouds that confirmed it was an anticyclonic storm. The moons of Jupiter, all 4 Galilean moons, were imaged at close range for the first time. Io appeared in the Voyager cameras as a body unlike anything anticipated. Its surface was not the heavily cratered terrain expected for a geologically old moon. It was bright, colorful, and geologically young-looking. But it was another image, not even taken for scientific purposes, that changed everything. Linda Morabito was a navigation engineer at NASA's Jet Propulsion Laboratory. Her job was to process the navigation images, photographs of known stars used to precisely determine Voyager 1's position in space. On March 8, 1979, 3 days after the Jupiter closest approach, she was examining a navigation image of Io, with the background stars overexposed to increase their visibility. In the overexposed image, she noticed an anomalous crescent-shaped feature beyond the edge of Io's disk. It took her several hours to rule out instrumental artifacts and background objects. What she was looking at was a volcanic plume, a column of volcanic gas and particles ejected from the surface of Io and extending 270 kilometers above the limb of the moon, caught in the sunlight at the precise geometry that made it visible against the black of space. The volcano was Pele. No one had ever seen a volcanic eruption on another world before that moment. The discovery was reported immediately. The Voyager imaging team reviewed the full dataset with new focus. Within days, 8 additional volcanic plumes had been identified in the imaging data. 9 active volcanoes on a single moon documented in a single flyby. The surface of Io was mapped in the images as heavily disrupted, colorful beyond any prior expectation, and entirely free of impact craters. 3 days before Morabito's discovery, on March 2, 1979, the journal Science had published a short paper by 3 scientists, Stanton Peele of the University of California, Santa Barbara, Patrick Casson and Ray Reynolds of NASA Ames Research Center, The paper's title was Melting of Io by Tidal Dissipation. Its abstract concluded with the prediction that Io should be the most intensely heated terrestrial body in the solar system, and that widespread active volcanism was the expected result. 3 days. The prediction and the confirmation were separated by 3 days. Peale and his colleagues had calculated the tidal heating rate for Io by combining the known orbital parameters, the eccentricity maintained by the Laplace resonance, the orbital period, Jupiter's mass, with material properties of rock under repeated stress. The mathematics pointed unambiguously toward an interior too hot to be geologically inactive. They submitted the paper before the flyby data was returned. They had no images to work from. They had equations, and the equations were correct. You are standing now, in the model of this story, in the version of events the script builds, on the surface of the observation, looking outward from Pelé's plume site toward the dark sky. The plume is above you, particles too small to see individually, but collectively forming a faint haze that catches the sunlight and diffuses it into something almost visible. The sulfur compounds in the plume are absorbing and re-emitting specific wavelengths. The ultraviolet detectors on Voyager 1, 25,000 kilometers away and retreating, are recording the plume's spectral signature in real time. The data is being encoded and transmitted back to Earth as radio waves at 8.415 gigahertz, broadcast from a transmitter aboard the spacecraft, producing 22 watts of power. The signal travels at the speed of light, 299,792 kilometers per second, and takes approximately 37 minutes to reach the receiving antennas of NASA's Deep Space Network on Earth. 22 watts, a power output less than a standard incandescent light bulb, carrying the first evidence of active volcanism on another world across hundreds of millions of kilometers of space. The receiving dishes on Earth are large, 26 meters and 64 meters in diameter, specifically because the signals arriving from spacecraft at these distances are extraordinarily faint. By the time the signal from Voyager 1 reaches Earth after traveling from Jupiter, the power level is on the order of 10 to the negative 16 watts, a tenth of a femtowatt. The amplifiers at the receiving stations must increase the signal by a factor of billions before it can be processed. And yet it works. It has always worked. The engineering that made it work was calculated precisely in advance, and the calculation was correct. Voyager 1 continued past Jupiter. Its closest approach to Io during the flyby was approximately 20,600 kilometers. At that distance, Io filled a substantial portion of the camera's field of view. The images captured at closest approach showed surface features as small as approximately 500 meters across, enough to resolve individual calderas, lava flow margins, and the boundaries of different sulfur deposit types. The data confirmed what the images at greater distance had suggested. Io was a world that had been completely transformed by internal heat. The caldera structures, the collapsed volcanic depressions, were numerous, varied in size, and varied in thermal state. Some were warm in the infrared, some were hot. A few registered temperatures that the instruments could barely quantify at the upper end of their measurement range. After the Jupiter encounter, Voyager 1's velocity had increased from approximately 10 kilometers per second to approximately 35.7 kilometers per second relative to the Sun through gravitational assist. The spacecraft had taken a small fraction of Jupiter's orbital momentum and converted it into kinetic energy. Jupiter's orbit was affected by an amount too small to express in any measurable unit. Voyager 1 was now moving fast enough to escape the sun's gravitational pull entirely. It was done with Io continue doing what it had always done. The plumes kept erupting. Loki Patera kept overturning its crust. The sulfur frost kept sublimating in sunlight and freezing in shadow. The mountains kept being compressed upward by the weight of their own resurfacing history. Jupiter kept pulling, and Io kept flexing, and the heat kept rising, and the surface kept being buried under fresh material, the craters disappearing under new layers of sulfur dioxide before they could be counted. No one would visit again for 16 years. But the questions Voyager left behind were not patient questions. They were the kind that forced the building of new spacecraft, the designing of new instruments, the calculation of new trajectories. The next spacecraft would go not past Io, it would stay. It would orbit. It would come back and back again, approaching closer each time, and it would spend years in the fire-lit neighborhood of the most volcanically active world in the solar system. That spacecraft was already being designed. Its name was Galileo. But before Galileo arrived, Voyager 2 made its own pass through the Jovian system. On July 9, 1979, 4 months after Voyager 1's encounter, Voyager 2 flew through Jupiter's neighborhood on a trajectory that brought it closest to the planet at a distance of 721,670 kilometers, farther than Voyager 1's closest approach, but still within range of detailed imaging. Voyager 2's cameras returned to Io with the same mission: observe the surface, document the volcanic activity, compare what had changed in 4 months. And things had changed. Paley, whose plume had been so dramatically visible in Voyager 1's navigation images, was no longer active, or more precisely, it was no longer producing a detectable plume at the time of Voyager 2's passage. The vent was still there. The dark ring deposit was still there, precisely where Voyager 1 had imaged it, but the column of material extending hundreds of kilometers above the surface, gone, temporarily as it turned out. Paley would be observed erupting again from ground-based telescopes in subsequent years, but its absence in the Voyager 2 data was the first evidence that Io's volcanic activity, while continuous across the moon as a whole, is not constant at any individual vent. Individual volcanoes on Io pulse. They intensify and diminish. Some erupt in discrete events, massive, brief, violently energetic outbursts, called outburst eruptions, that can increase Io's total thermal output by several percent in a matter of hours. Others, like Prometheus, maintain a low, steady output across decades. The full range of volcanic behavior that Io exhibits spans from barely above background thermal anomalies to eruptions energetic enough to be detected by Earth-based telescopes as brightening events in Io's reflected light. The largest outburst eruptions on Io are classified as Ionian-style eruptions, a category of volcanic event that may have occurred on the early Earth during the Archean Eon, when terrestrial heat flow was higher and the crust was thinner, but that no longer occurs anywhere on Earth today. In these events, large volumes of ultramafic magma, iron and magnesium-rich silicate melts at temperatures above 1,400 degrees Celsius, erupt rapidly, spreading across the surface in thin, fast-moving flows that can cover hundreds of square kilometers in hours. The temperatures measured in some Ionian outburst eruptions exceeding 1,600 degrees Celsius, are higher than any lava temperature recorded anywhere on Earth in the modern era. They are consistent with comatite lavas that erupted on the early Earth between 2.5 and 3.5 billion years ago, when the mantle was hotter than it is today. Io's magmatism, driven by tidal rather than radiogenic heat, has maintained conditions on its surface that resemble Earth's earliest geological era, preserved and sustained in perpetual operation for 4.5 billion years. You are above the surface now, in the observational position that this story grants you, and the data streaming from Voyager 1's instruments as it retreated has been fully processed and cataloged on Earth. The scientific community in 1979 and 1980 was absorbing a revised picture of what the solar system actually is, not a collection of geologically dead, cratered rocks orbiting a star, but a dynamically active system in which even distant moons can maintain interior heat engines through purely gravitational mechanisms. The implications extended beyond Io immediately. Europa, the next moon outward, was also part of the Laplace resonance. Its tidal heating was lower, Europa's orbital eccentricity is smaller, and it is farther from Jupiter, so the tidal forces are weaker. But the models suggested that Europa should still be warm inside. Warmer, perhaps, than its icy surface implied. The Voyager images of Europa had shown a surface covered in ice, smooth, crisscrossed with brown-stained fractures, but with very few craters and none of the chaotic topography expected from a dead, frozen world. The ice on Europa, the models now suggested, might be floating on liquid water, a subsurface ocean kept liquid by residual tidal heating kilometers below the ice shell. The same mechanism that was incinerating Io's interior might be maintaining a liquid ocean on Europa, an ocean that would represent the largest body of liquid water in the solar system outside of Earth, and potentially a habitat for life. This was not confirmed in 1979. It would take another 2 decades and the Galileo spacecraft's magnetic field measurements to make the liquid ocean hypothesis strongly supported. But the intellectual thread ran directly from Io's volcanic heat to Europa's possible ocean, and that thread was visible to planetary scientists immediately after Voyager 1's encounter. The Laplace resonance was not just a gravitational curiosity, it was a planetary engine. It was driving geological activity across multiple moons simultaneously, at different intensities. Io was the most extreme case. Europa was the subtlest. Ganymede, the largest moon in the solar system at roughly 5,268 kilometers in diameter, larger than the planet Mercury, also showed evidence of tidal heating in its geological past, though its current heat flow was low enough that its surface had frozen and solidified. 3 moons, 1 resonance, 3 different geological outcomes. You let that settle as you drift above the terminator of Io, the line between day and night. On this world is not soft, the way twilight is soft on Earth. The atmosphere is too thin to scatter light. On Earth, the sky begins to brighten tens of minutes before sunrise, because molecules in the atmosphere scatter sunlight over the horizon before the sun itself clears it. On Io, there are not enough atmospheric molecules to scatter light significantly. The transition from sunlit surface to shadowed surface is sharp, almost geometric. Step from light to shadow, and the temperature drops precipitously within seconds as the surface loses contact with solar radiation and the thin atmospheric contribution evaporates. Inside the shadow, in the eclipse that Io enters, for approximately 2 hours every 1.769 days. As it passes behind Jupiter, the atmosphere collapses, the surface temperature falls, the sulfur dioxide frost, which had been sublimating slowly in sunlight, contributing a trickle of gas to the thin atmospheric column above, stops sublimating. The atmospheric pressure drops further still. And in the eclipse, something else becomes visible that cannot be seen from the sunlit side. The plasma torus. Io orbits inside one of the most intense radiation environments in the solar system outside of the sun itself. Jupiter's magnetic field, generated by convection of metallic hydrogen deep within the planet's interior and approximately 20,000 times stronger than Earth's magnetic field at the surface, extends far beyond the planet. The field's equatorial plane, tilted about 10 degrees from Jupiter's rotational equator, sweeps around as the planet rotates once every 9.925 hours. Io orbits within this field. As Io's volcanic plumes inject approximately 1 ton of material per second into the space around the moon, primarily sulfur dioxide, sulfur, oxygen, and sodium, Jupiter's magnetosphere strips electrons from these atoms, creating ions. The ions are then caught by Jupiter's magnetic field, and because they are charged particles in a magnetic field, they are constrained to move in ways determined by the field's geometry. They spread around Io's orbit, filling a torus-shaped volume, a donut centered on Io's orbital path. This structure is called the Io plasma torus. It extends roughly 2 Jupiter radii to either side of Io's orbital plane and completely encircles Jupiter at Io's orbital radius. The torus contains sulfur and oxygen ions moving at velocities of tens of kilometers per second, driven by both Jupiter's co-rotating magnetic field and the temperature of the plasma itself, which reaches tens of thousands of degrees. The current flowing between Io and Jupiter through the plasma torus, the Io flux tube, carries approximately 5 million amperes of electrical current. 5 million. By comparison, a typical lightning bolt on Earth carries between 5,000 and 20,000 amperes, and only for a fraction of a second. The Io flux tube is a permanent, sustained current of 5 million amperes connecting Io to Jupiter's polar regions, flowing continuously as long as Io moves through Jupiter's magnetic field, which is always. This current is what produces the Io-related auroral footprint on Jupiter. When energetic electrons travel down the flux tube and strike Jupiter's upper atmosphere, they excite atmospheric molecules that then emit light, an aurora, but not at Jupiter's polar oval, a separate bright spot fixed in position relative to Io's location, tracking around Jupiter's disk at the same rate that Io orbits. From Earth, this footprint aurora is visible in ultraviolet wavelengths with the Hubble Space Telescope, a small glowing mark on the face of Jupiter that tells observers exactly where Io is in its orbit without having to look directly at Io. The plasma torus itself glows. In visible light, it is faint, but it has been photographed from Earth by telescopes, sensitive enough to capture it. A reddish-pink ring around Jupiter, visible when Jupiter is observed away from full opposition. The color comes primarily from sulfur ion emission lines. The torus is the most visible evidence, from a distance, that Io is continuously losing material to its environment, that the volcanism that reshaped Io's entire surface is also actively feeding a structure hundreds of thousands of kilometers across, a cloud of ionized gas that surrounds the largest planet in the solar system. Io is not merely a geological object. It is an engine with outputs that extend across the entire Jovian system. Now you breathe. The information accumulates, and some part of you processes it, not as data, but as image. A world lit from below, painted in sulfur, surrounded by a ring of fire that extends from its orbit outward across a vast magnetized space. A moon smaller than our own moon, heated by the gravity of a world 317 times Earth's mass, producing enough energy to reshape its own surface on timescales shorter than human civilization. Voyager 1 had seen this world for 37 hours at close range. It had seen 9 volcanoes. It had measured temperatures and taken spectra and recorded the plasma environment and transmitted everything back across hundreds of millions of kilometers on 22 watts of power. The data was enough to change the textbooks. It was not enough to answer the deeper questions. How thick is Io's crust precisely? What is the depth of the magma ocean? How often do the largest outburst eruptions occur, and what triggers them? How does the surface change between eruptions? What happens at the interface between the silicate magma and the sulfur-rich surface deposits? What is the exact composition of the lava flowing from the hundreds of active vents? These questions required a spacecraft that could stay, one that could orbit Jupiter and return to Io repeatedly with instruments refined by the knowledge gained from Voyager. It took 23 years from Io's discovery by Voyager's cameras to the mission that would answer many of these questions. Years of planning, years of budget negotiations, years of engineering development. The spacecraft that finally arrived at Jupiter in December 1995 carried a scientific payload specifically designed for the questions Voyager had raised and could not answer. It was named for the man who had first seen Io in 1610, who had written it down in his notebook as a small point of light near Jupiter, and noted the next night that it had moved, and understood within weeks that what he had seen was a world orbiting another world. Galileo. The spacecraft arrived, and the questions began to be answered, one flyby at a time, closer and closer, pushing deeper into the fire. The Galileo spacecraft launched from Earth on October 18, 1989, not from a launch pad in the conventional sense, from the cargo bay of the Space Shuttle Atlantis in low Earth orbit, released into space from a platform already moving at 7.7 kilometers per second. From there, an attached booster called the IUS, the inertial upper stage, fired to push Galileo onto its interplanetary trajectory. The path to Jupiter was not direct. Galileo did not have enough propellant to travel to Jupiter on a straight line from Earth because no rocket large enough to put it on that trajectory existed at the time. Instead, the mission designers used the same gravitational assist technique that had accelerated the Voyager spacecraft, but applied it multiple times within the inner solar system. Galileo flew past Venus once and Earth twice before it had accumulated enough velocity to reach Jupiter. The journey took 6 years. The spacecraft that finally crossed into the Jovian system in December 1995 had been traveling since Reagan was in the White House. On December 7, 1995, Galileo fired its main engine for 49 minutes and 20 seconds to slow itself enough to be captured by Jupiter's gravity. This was the most critical maneuver of the entire mission. If the engine had failed to fire, or had fired for too short a time, Galileo would have flown past Jupiter and continued into deep space, and the mission would have been over. The engine fired, The deceleration was precisely as calculated. Galileo became the first spacecraft ever to enter orbit around Jupiter. The orbital insertion placed Galileo into a highly elliptical orbit that brought it close to Jupiter on each pass, and then flung it far out into the Jovian system on the other side. Over the following 8 years, mission controllers at JPL adjusted the orbit repeatedly using gravitational assists from Jupiter's own moons, particularly Ganymede and Callisto, to reshape the trajectory and bring the spacecraft into proximity with different targets at different times. Io presented a special problem. Io sits inside the most intense region of Jupiter's radiation belts. The radiation environment near Io's orbit is not merely hostile to human biology, it is actively destructive to electronics. Charged particles trapped in Jupiter's magnetic field, primarily electrons and protons, bombard anything in that region at energies that can penetrate shielding, disrupt electronic memory, damage sensors, and corrupt data. The dose of ionizing radiation that a spacecraft receives at Io's orbital distance from Jupiter is orders of magnitude higher than what satellites in Earth orbit experience. The Galileo spacecraft was designed with radiation-hardened electronics, but the level of hardening achievable in the 1980s, when the spacecraft was built, had limits. The mission designers made a deliberate choice early in the mission: keep Galileo away from Io during the primary mission phase, concentrate on the outer moons and Jupiter's atmosphere, and save the Io flybys for the extended mission, when the spacecraft had already accomplished its primary science objectives and the accumulated radiation damage was an accepted risk. For the first 2 years of the mission, Galileo did not fly close to Io. It flew past Ganymede 6 times, Callisto 8 times, Europa 11 times. It watched Io from a distance, measuring its thermal output, tracking its plasma torus contribution, documenting changes in the sulfur dioxide atmosphere. But it did not go close. The extended mission began in 1997, the Galileo Europa mission, and then the Galileo Millennium mission, pushed the spacecraft into riskier trajectories. By 1999, Galileo was finally cleared for close Io encounters. On October 11, 1999, it made its first close flyby of Io since the brief distant pass during orbital insertion 4 years earlier. The flyby designation was I-24, the 24th orbit of the mission, Io targeted. You are aboard Galileo now, in the sense that this narrative allows. The instruments are your senses. The spacecraft is your vehicle. And on October 11th, 1999, you are descending toward Io at a closest approach distance of 611 kilometers above the surface. 611 kilometers, closer than most satellites orbit the Earth. The NIMS instrument, the near-infrared mapping spectrometer, is scanning the surface below, recording the thermal emission from individual volcanic features. The spatial resolution at this distance is sufficient to resolve features a few kilometers across, close enough to map the boundaries of individual lava flows, to see the temperature gradient from the center of a caldera to its cooled margins, to distinguish the freshly erupted high-temperature material from the older, crusted-over surfaces adjacent to it. The surface below is not what the sulfur-tinted global views suggest. At close range, Io's surface is textured and complex. The sulfur plains are not flat, they are subtly rolling, marked by low ridges and shallow depressions that record the flow history of successive lava floods. The calderas are not simple holes. They have internal structure, terraced walls, floor units at different elevations suggesting multiple collapse events at different times. The mountains are not smooth. They are fractured along their flanks, scarred by mass-wasting events where the steep slopes shed material in Ionian landslides under the moon's 1.8 meters per second squared gravity. Loki Patera is below you now, its 200-kilometer wide surface registering in the NIMS data as a patchwork of temperatures. The inner portions of the lake are warmer, freshly exposed lava, overturned within the past few months, the thin solidified crust still radiating heat at temperatures between 300 and 600 degrees Celsius above the surrounding surface. The margins are cooler, where older crust has had more time to radiate energy away. The boundary between warm and cool traces a rough arc across the lake surface, and this arc is the edge of the thermal wave that Voyager's data first suggested, and Galileo is now measuring directly. The wave propagates. It has been doing so since before Voyager 1 arrived, and will continue after Galileo is gone. The overturning of Loki Patera's surface crust is not a random process. It is a physical consequence of the density difference between the cooled, solidified surface crust and the hot, less dense liquid lava beneath it. As the crust thickens and cools, it eventually becomes dense enough to sink, to founder in geological terminology. And when it does, fresh hot magma from below fills the gap. The process propagates laterally as the foundering crust pulls adjacent sections down, creating the wave that moves clockwise around the lake's perimeter. This is the same mechanism by which the seafloor of Earth's oceans overturns at subduction zones, dense old oceanic crust sinking beneath less dense continental material, but compressed into a 200-kilometer lake and cycling through on a timescale of months rather than millions of years. On November 26, 1999, 46 days after the I-24 flyby, Galileo returns to Io. This is the I-25 flyby. The closest approach is 300 kilometers, closer than before, deep inside the radiation belts, the instruments recording as fast as their design allows, the onboard tape recorder storing data that will take months to fully downlink to Earth. At 300 kilometers, individual features on Io's surface are resolved at scales of a few hundred meters. The cameras are not optical in the conventional sense. They are solid-state imaging devices, CCDs, sensitive to visible wavelengths, and at 300 kilometers, the images they return show Io's surface in a detail no human instrument had previously achieved. The region around Prometheus is visible in these images with clarity sufficient to trace individual flow margins. The lava flow emanating from Prometheus's active vent site has advanced measurably since the Voyager 1 images taken 20 years earlier. The flow front has moved approximately 75 to 95 kilometers to the west over those 2 decades, a rate of roughly 3 to 5 kilometers per year. This is a slow lava flow by volcanic standards, but sustained, uninterrupted for at least 20 years, possibly much longer. The Prometheus plume itself appears in the I-25 images as a faint haze above the vent site. At 300 kilometers altitude, the spacecraft is below the top of the plume, which reaches 100 kilometers, but above the surface. The geometry means that Galileo is flying through the outer margins of the Prometheus plume during this pass. The instruments record the composition of the plume material directly. Sulfur dioxide dominates, with smaller concentrations of elemental sulfur and trace amounts of hydrogen sulfide. The particle density within the plume at 300 kilometers altitude is too low to affect the spacecraft's trajectory measurably, but high enough to register in the mass spectrometer. You are passing through the outer edge of a volcanic eruption on another world. The data streaming into the recorder is compressed, prioritized, organized by instrument team protocols established years before launch. The highest priority data, thermal maps, close-range surface images, plasma measurements, is recorded first, on the assumption that if the tape recorder fills before all data is captured, the most valuable observations are preserved. The tape recorder on Galileo is not a metaphor. It is a literal magnetic tape drive, a device containing a reel of magnetic recording tape, spinning at controlled speed, with read and write heads that store data as patterns of magnetization. The technology was mature and reliable, the best available when Galileo was designed in the late 1970s and early 1980s. It had one known vulnerability. The energetic particles in Jupiter's radiation belts could flip individual bits in the magnetic recording, corrupting data, occasionally corrupting the spacecraft's own software memory. By the time of the Io flybys, the tape recorder had experienced significant radiation damage. It could no longer rewind reliably to the very beginning of the tape. Mission controllers managed it carefully, tracking which sections of tape were still reliable, recording to safe regions, playing back data slowly over the weeks between flybys. The Deep Space Network antennas on Earth, the 70-meter dish at Goldstone, California, the equivalent dish at Canberra, Australia, the 70-meter antenna near Madrid, Spain, maintained near continuous contact with the spacecraft, receiving its downlinked data at rates between 10 and 160 bits per second, depending on the distance and antenna configuration. 160 bits per second. A standard home internet connection in 2024 operates at tens to hundreds of millions of bits per second. Galileo, transmitting its close-up images of Io's surface across distances of hundreds of millions of kilometers, transmitted data at a rate slower than a 1980s dial-up modem. And every bit mattered. The I-27 flyby occurs on February 22, 2000. Closest approach, 198 kilometers above Io's surface. This is the deepest penetration of the Galileo mission into Io's vicinity, 198 kilometers, less than the distance from one major city to another on Earth, separated from the surface of the most volcanically active world in the solar system by a gap smaller than the width of some of Earth's largest mountain ranges. At 198 kilometers, the magnetic field measurements taken by Galileo's magnetometer reveal something that had not been clearly established by Voyager. Io does not have a significant intrinsic magnetic field. The planet-sized magnetic fields seen at Ganymede, which generates its own magnetosphere, are absent at Io. The Moon exists entirely within Jupiter's field, embedded in it, contributing to it through its plasma torus, but generating essentially no field of its own. This is consistent with models of Io's interior. A global magnetic field requires a convecting, electrically conducting fluid interior, typically an iron core that is at least partially liquid and in motion. Earth's magnetic field is generated by convection in the outer core, a layer of liquid iron and nickel surrounding the solid inner core. Io's core, heated as it is by tidal dissipation, may be liquid, but the tidal heating also tends to suppress the kind of organized convection that generates a magnetic field. The tidal forces drive heat upward in a relatively uniform way, rather than creating the temperature-driven convective cells that a dynamo requires. The absence of a magnetic field means Io has no magnetospheric protection from Jupiter's radiation environment. The surface is irradiated directly by the charged particles in Jupiter's radiation belts. The sulfur dioxide atmosphere absorbs some of this radiation. UV photons and energetic particles interact with SO2 molecules, breaking them apart, contributing to the production of atomic sulfur and oxygen that then recombine or escape into the plasma torus. But the atmosphere is far too thin to shield the surface meaningfully. Any material on Io's surface, rock, sulfur compounds, theoretical organic molecules, is continuously bombarded by radiation at intensities that would be lethal to any known Earth organism within minutes. The radiation environment at Io is one reason it is not considered a candidate for biological life, despite its vast energy output. Energy alone is not sufficient for life. Life as understood by biochemistry also requires liquid water, organic molecules, and environments where those molecules can interact over time without being destroyed by radiation or thermal extremes. Io's surface provides energy in extraordinary abundance and liquid water in none. Its surface temperatures range from -130 degrees Celsius to over 1,600 degrees Celsius within the same hemisphere. Its radiation environment is destructive to complex chemistry. Its atmosphere is too thin and too variable to support any known biochemical process. Io is not a world for life. It is a world that demonstrates what planets do with energy when life does not exist to mediate it. The surface you are passing over at 198 kilometers is a record of that unmediated energy. Every caldera, every lava flow margin, every sulfur deposit is the direct product of tidal heating finding its way to the surface through the most direct route available. No biology intercedes. No carbon cycle moderates the heat flux. No ocean buffers the temperature extremes. The physics operates without negotiation. South of the equator, in the region Galileo's cameras are resolving at their closest range yet, a structure appears that has no obvious equivalent on Earth. It is a shield-shaped edifice approximately 300 kilometers across, rising gently from the surrounding plain to a maximum elevation of roughly 1.5 kilometers above the base level. Its summit is marked by a caldera complex, multiple collapsed depressions arranged in a cluster, each one the remnant of a subsurface chamber that emptied during an eruption event and left its roof unsupported. This is Loki Patera, one of dozens of such shield structures that Galileo is documenting across Io's surface. The mountains of Io, seen at 198 kilometers, are not gentle features. The scarps on their flanks are steep, in some cases nearly vertical for hundreds of meters, and the talus piles at their bases record mass wasting events that have occurred recently, enough to be unburied by volcanic deposits. At the mountain called Tohill Mons, which rises approximately 8.6 kilometers above the surrounding surface, the southern flank shows a massive gravitational collapse scar, a region where a section of the mountain's slope gave way and slid downhill, leaving an irregular depression at the summit and a debris field at the base. The event that caused this collapse left no identifiable remnant, no trigger crater, no obvious intrusion site, only the scar and the deposit. Tohill Mons is instructive because it rises not from a volcanic vent, but from a region of the crust that has been compressed and buckled by the weight of resurfacing. The mountain is not a volcano. Its summit shows no active thermal anomaly in the NIMS data. It is a mechanical consequence of geology operating on a world that is constantly burying itself and constantly adjusting to the added weight. On August 6, 2001, Galileo executes the I-31 flyby. Closest approach, 194 kilometers, fractionally closer than I-27. The instruments are degraded. The radiation accumulated over the mission has affected the sensitivity of several detectors, and some wavelength channels of the NIMS spectrometer have ceased functioning. But the cameras still work, and the magnetometer still works, and the plasma instruments still work. The I-31 data reveals a new large-scale eruption that has begun on Io's anti-Jovian hemisphere, the side facing permanently away from Jupiter, in a region called Loki Patera. Loki had shown activity in earlier flybys, but the I-31 images capture something different: a curtain of lava, not a point vent, not a caldera filling with magma, a fissure eruption, a long crack in the surface from which lava is erupting along its entire length simultaneously, producing a wall of fire several kilometers long and several hundred meters high. The temperature of this lava curtain, as recorded by NIMS at its closest range, exceeds 1,600 degrees Celsius in its hottest regions. This places it firmly in the category of ultramafic eruption. The high-temperature, iron and magnesium-rich volcanic events that define Ionian-style volcanism. The eruption is spreading lava across the surrounding surface at rates that, extrapolated from the thermal data, suggest flow advance speeds of meters per minute, slow enough to watch from a safe distance, fast enough to completely resurface a large area within days. You are watching this from 194 kilometers, your instruments recording in real time, the data queuing on the damaged but still functional tape recorder, waiting for the slow downlink to Earth that will bring this image to human eyes months later. The last close Galileo flyby of Io is designated I-32. It occurs on January 17, 2002. Closest approach, 102 kilometers above the surface. 102 kilometers. The spacecraft descends to within 102 kilometers of a world that is erupting at multiple points simultaneously, that is surrounded by a plasma environment hostile to the very electronics carrying out the observation that has been absorbing radiation for 6 years beyond what its design lifetime anticipated. At 102 kilometers, Io's surface occupies a substantial arc of the view from the spacecraft. The horizon curves visibly. Individual calderas span significant fractions of the camera's field of view. The thermal data is at its highest spatial resolution of the entire mission, and the spacecraft survives. Galileo's mission ends not with a close approach that damages it beyond function, but with a deliberate final act 18 months later. On September 21st, 2003, mission controllers at JPL send the final command sequence to Galileo and aim it at Jupiter. The spacecraft enters Jupiter's atmosphere at a velocity of approximately 50 kilometers per second and is destroyed by atmospheric friction and pressure within seconds. The decision was intentional to prevent any possibility that a spacecraft carrying Earth biological contamination might eventually crash onto Europa, whose subsurface ocean is considered a potential habitat for life. Galileo died to protect a world it had helped discover. The data it returned, thousands of images, years of thermal maps, magnetic field profiles, atmospheric measurements, plasma observations, established Io as a fully characterized world. Not a mystery with a name, but a place with measurable properties, understood mechanisms, quantified outputs, the total heat flow from Io's interior, the depth of the magma ocean, the behavior of individual volcanic systems across years of observation, the composition of the atmosphere and plasma torus, the structure of the mountains and their formation mechanism. All of this came from Galileo's 8 years in the Jovian system. But Io did not stop after Galileo left. It kept erupting, it kept burying its surface. Loki Patera kept overturning. Prometheus kept advancing its flow front. Pele kept building its red ring, molecule by molecule, plume emission by plume emission. The plasma torus kept glowing. The flux tube kept connecting Io to Jupiter's poles, uninterrupted. From Earth, astronomers tracked Io through the late 2000s and 2010s using large ground-based telescopes, the Keck Observatory, the Gemini Observatory, the Very Large Telescope in Chile, equipped with adaptive optics systems that partially corrected for atmospheric blurring, allowing resolution of Io's disk and detection of individual thermal hotspots. Ground-based observers documented outburst eruptions, brief, intense events in which Io's infrared brightness spiked dramatically over periods of hours to days before fading, occurring at rates suggesting one major outburst every 1 to 3 years. One such outburst, documented in August 2013 by multiple observatories, produced a thermal emission that made Io briefly the brightest object in the near-infrared sky at wavelengths around 3.8 micrometers, brighter than Jupiter, brighter than any other body in the solar system except the Sun itself. For the duration of the event, the eruption involved approximately 50 square kilometers of fresh lava surface at temperatures exceeding 1,300 degrees Celsius, spreading across a region of Io's surface in an event that, had it occurred on Earth, would have been among the largest volcanic episodes in geological history. And it happened on a moon most people cannot find on a map. The quiet of the observation continues. You are still here, in the position this narrative grants you, watching a world that is never quiet from a vantage point that allows you to hold its entire history in a single view. 16 years of Galileo data, Voyager data from 1979, ground-based monitoring across decades, and now something new approaching from the direction of the inner solar system, a spacecraft launched in 2011, designed primarily to study Jupiter's magnetic field and interior structure, now being turned in its extended mission to look more closely at the moons. Its name is Juno. By 2021, Juno's primary science mission, the mapping of Jupiter's gravitational and magnetic fields, was largely complete. The spacecraft had survived 40 orbits of Jupiter, each one cutting through the intense radiation environment near the planet, each one delivering new measurements of the magnetic field structure and atmospheric dynamics. NASA approved an extended mission that redirected Juno toward Jupiter's moons, scheduling close flybys of Ganymede, Europa, and Io across the following years. The Io encounters were planned for late 2023 and early 2024. Juno's instruments included the Jovian Infrared Aureole Mapper, JRUM, an infrared camera and spectrometer sensitive to wavelengths between 2 and 5 micrometers, ideally suited for measuring the thermal emission from volcanic features. It also carried a microwave radiometer, a stellar reference unit used for navigation, and the JunoCam, a wide-angle color camera originally designed as a public outreach instrument, but increasingly used for science. On December 30th, 2023, Juno executed the JM57 flyby of Io closest approach, 1,500 kilometers, not as close as Galileo's final pass at 102 kilometers, but equipped with instruments far more sensitive than anything Galileo carried, taking advantage of 30 years of detector technology development since the Galileo spacecraft was designed. The JERM data from the JM57 flyby returned thermal maps of Io at resolutions sufficient to characterize individual hotspot temperatures across the entire sunlit hemisphere in a single observation. The total number of distinct thermal anomalies, active volcanic features, identified in the JM57 data was in excess of 50, scattered across both hemispheres, varying in intensity from barely above background warmth to the blazing signatures of actively erupting calderas. On February 3, 2024, Juno returned to Io for the JM58 flyby. This time, closest approach was approximately 1,500 kilometers again, consistent with the December flyby, but the geometry was different, bringing different regions of Io's surface into close view. The JunoCam images returned from this flyby showed Io's polar regions in detail not previously achieved. The polar terrain is different from the equatorial and mid-latitude surface, less dominated by large calderas and lava plains, more marked by isolated mountains and irregular depressions with sulfur dioxide frost deposits concentrated in the permanently shadowed floors of high-latitude basins where sunlight never reaches at sufficient angle to cause sublimation. You are with Juno now, in this moment of the story that steps carefully between what instruments have measured and what that measurement means to experience. The approach to Io at 1,500 kilometers is fast. Juno is in a highly elliptical orbit around Jupiter, and its velocity relative to Io during the flyby is on the order of kilometers per second. The closest approach window, the brief period during which the spacecraft is within 2,000 kilometers, lasts only a few minutes. In those minutes, JERM is scanning continuously. JunoCam is taking sequential images. The magnetometer is recording the local field, and the plasma instruments are measuring the particle environment. Below you, as you pass through that window, Loki Patera is visible in the thermal data as the largest and hottest continuous feature on the hemisphere facing Juno. Its 200-kilometer expanse is still overturning. The thermal wave that Galileo measured in the late 1990s is still propagating, its clockwise circulation still completing its 540-day cycle, unchanged in character, if not in precise timing. Pele is on the opposite hemisphere during this pass, not directly observable, but Prometheus is visible, its plume rising 100 kilometers above the surface, confirmed still active as it has been for at least 45 years of continuous observation. 45 years. Longer than most human institutions, longer than most careers, longer than the gap between Voyager 1 and the Juno extended mission. Prometheus has been erupting continuously for the entirety of the human spaceflight era. The total heat output from Io's surface, as compiled from Juno's JERM measurements, combined with prior Galileo and ground-based data, confirms the earlier estimate, approximately 100 terawatts, consistent with the tidal heating models, confirming that the energy budget for Io is fully accounted for by the Laplace resonance-driven tidal dissipation mechanism. The heat is not diminishing, the resonance is not weakening. The system is in a steady state that has persisted for billions of years and will continue for billions more, unless the orbital configuration of the Jovian system changes. There is one scenario in which it does change. The Laplace resonance is not perfectly rigid. Over very long timescales, tens of millions to hundreds of millions of years, the eccentricity of the resonant orbits can change as the resonance exchanges energy with the longer period orbital dynamics of the outer Jovian system. Models of Io's long-term thermal evolution suggest that the current high heat flow state may be episodic, that Io alternates between periods of intense volcanic activity and periods of relative quiescence as the orbital eccentricity waxes and wanes on geological timescales. If this is correct, the Io you are observing now, the maximally volcanic, heat-flooded, crater-free world that Voyager first revealed, may not represent Io's average state. It may represent a peak, a moment of maximum tidal energy dissipation, geologically brief, that will eventually subside as the orbital configuration shifts and the eccentricity decreases. In a lower eccentricity state, Io's tidal heating would diminish, the volcanic output would decrease, craters would begin to accumulate on the surface as resurfacing slowed. The plasma torus would thin as the source material from volcanic plumes decreased. The flux tube current would weaken. The Io footprint aurora on Jupiter would dim. Io would become, for a geological period, quieter. And then, as the resonance shifted again and eccentricity rebuilt, the fires would return. This cycle, if it occurs, is not observable on human timescales. No instrument will watch it happen. No spacecraft will document the transition. It exists only in the mathematics of orbital mechanics and the models built from them, the same mathematics that allowed Peale, Casson, and Reynolds to predict what Voyager would find before the spacecraft arrived. The mathematics is the deepest knowledge available, and the mathematics says that Io has been doing this in some form since the Jovian system formed. For 4.5 billion years, the resonance has held. The tidal forces have flexed the interior, the heat has risen to the surface, the volcanoes have erupted, and the surface has been continuously, completely renewed. If you could stand at a single point on Io's surface and watch, not for a human lifetime, but for a geological one, you would see the ground beneath you covered, layer by layer, in new material. Sulfur dioxide frost would settle from above during quiet periods. Lava flows would arrive from the direction of the nearest caldera and cover the frost, cool, crack, and be covered in turn by the next flow. The plume from Pele would deposit its red sulfur allotropes over everything within 1,000 kilometers. During each major eruption, the mountains would grow taller as the weight of new material compressed the lower crust, and occasionally a mountain's flank would fail, and a landslide would redistribute the accumulated mass across a nearby plain. Over thousands of years, the surface you started on would be meters below the current level. Over millions, tens, or hundreds of meters, the rock you stood on at the beginning would be deeply buried, compressed, heated by the insulating overburden and by the magma circulating below, eventually remelted and recycled back into the system that erupted it in the first place. Io is a world that consumes itself and rebuilds itself continuously, without pause, on a timescale that makes human history invisible. The connection between Io's volcanic output and Jupiter's atmosphere is not abstract. It is measurable, quantified, and visible. Every second, Io's volcanoes inject approximately 1 ton of volcanic material per second into the space around the Moon. This gas is immediately subjected to Jupiter's intense radiation environment. Ultraviolet photons and energetic particles strip electrons from the molecules, producing ions that are captured by Jupiter's magnetic field and swept into the plasma torus that surrounds Io's orbit. The total power deposited into Jupiter's upper atmosphere by the Io flux tube current is estimated at approximately 2 trillion watts, 2 terawatts, sustained continuously. This is roughly equivalent to the entire electrical power generating capacity of the United States, running without interruption, powered entirely by the tidal interaction between Jupiter and a moon 421,700 kilometers away. Now, let the instruments step back. The story permits something Juno cannot do. It permits a different perspective, not the perspective of a sensor scanning at infrared wavelengths from 1,500 kilometers, but something closer than any instrument has gone. The perspective of standing on the surface itself. You are on Io, not beside Prometheus, where the ground is warm from the advancing lava flow, but the immediate surface is sulfur dioxide frost, pale yellow underfoot, crunching with a vibration you feel through the soles of your suit rather than here, because the atmosphere is far too thin to carry sound to your ears. You are not there. You are at the western margin of Loki Patera. The ground beneath you is old crust, solidified lava, cooled over the past several months since the thermal wave last passed through this section of the lake margin. It is dark gray, almost black, fractured into irregular polygons by the thermal contraction that occurred as it cooled. The surface is not flat. It is subtly buckled, raised at the polygon edges where the contracting crust pulled itself into shallow ridges, depressed at the centers where the material pulled inward as it shrank. Beneath this crust, approximately 10 to 30 meters below your feet, magma is still liquid. The thermal gradient from surface to subsurface is steep. The surface temperature here, away from the active overturning zone, is approximately 300 degrees Celsius. Your suit handles this. The instruments embedded in the suit material are recording it, logging the temperature, calculating the heat flux. To your east, the edge of the active overturning zone is visible as a line of brighter, yellower light. Not the yellow of sulfur, the yellow of incandescence, lava at temperatures above 800 degrees Celsius, glowing in the wavelengths your eyes are sensitive to, shimmering against the black sky. The line is not straight. It curves and breaks, following the irregular boundary where the old crust has foundered and the fresh magma has welled up to replace it. The thermal wave is moving toward you, slowly. At the rate of meters per day, the active zone advances as the older crust ahead of it, the crust you are standing on, thickens and cools to the density at which it will sink. You are standing on ground that will, within months, begin to founder. The magma beneath your feet will rise through the cracks that form as the crust breaks apart, and this surface will be buried under a new layer of fresh lava. There is no wind, there cannot be wind. The atmosphere is too thin for bulk gas motion to constitute wind in any aerodynamic sense, but there is motion in the gas above the surface. Sulfur dioxide sublimating from frost deposits on the surrounding plain creates a slow diffusion of gas molecules above the surface, a drift too dilute to feel but measurable by the suit's pressure sensors. The partial pressure registered is 0.3 nanopascals, 3/10 billionths of a pascal. Above you, the sky is black, not the transitional black of a mountaintop at night on Earth, where the atmosphere still scatters enough light to make the sky a deep blue black and the stars compete with the horizon glow. This is a different black. An absolute black because there is no atmosphere to scatter anything. The stars are the same stars visible from Earth, the same patterns, the same brightnesses, but without any atmospheric shimmer, without any turbulence. They do not twinkle. They are fixed and hard and permanent. And filling a significant arc of the sky above the western horizon is Jupiter. It is large, profoundly disorienting large. Jupiter's angular diameter, as seen from Io, is approximately 19.5 degrees, about 39 times the angular diameter of the full moon, as seen from Earth. It is not a point, it is not a disk. It is a presence that occupies a full quadrant of your sky, banded in cream and tan and pale orange. The equatorial bands parallel to the horizon, the great red spot, currently on the hemisphere facing away from you, but its absence in the visible disk still notable because you know it is there, rotating around on the other side. The planet does not rise, it does not set, because you are standing on the Jupiter-facing hemisphere of a tidally locked moon. Jupiter is fixed in the sky, drifting by only a fraction of a degree north and south over the course of Io's orbit, as the slight inclination of the orbital plane changes the viewing angle. For all practical purposes, Jupiter is stationary above the western horizon. It has been there since Io formed. It will be there long after every surface feature you can see has been buried and rebuilt multiple times. The light from Jupiter falls on the landscape around you with enough intensity to cast shadows. The illumination is reflected sunlight. Jupiter itself emits almost no visible light, though its thermal emission in the infrared exceeds what it receives from the sun, because the planet is still slowly contracting and releasing gravitational potential energy. But the reflected sunlight is enough. The frozen sulfur dioxide plain to your north, the dark crust of Loki Patera's margin beneath your feet, the distant ridgeline of an unnamed compressional mountain to the south, all of it is lit by Jupiter-reflected light in the intervals when the sun is below your horizon. Right now, the sun is above the horizon. It appears not as the broad, warm disk visible from Earth, but as a small, brilliant point, far diminished in angular size, still too bright to look at directly, but concentrated into a point rather than a disk, giving it an intensity per unit angle that is blinding. The combination of sunlight and Jupiter light illuminates the landscape in two different directions simultaneously. Shadows from the two sources fall at different angles, doubling the shadow of every rock and ridge, and giving the surface a slightly uncanny illumination that no landscape on Earth ever has. The thermal wave to your east advances by another unmeasurable increment. Somewhere beneath the crust to your south, a pocket of magma is accumulating pressure. You do not know this from sight. You know it from the seismometer reading in your suit, which is detecting low-frequency vibrations below 1 Hz, propagating through the crust from a source a few kilometers away. These vibrations are consistent with what volcanologists call harmonic tremor, the resonance of a fluid-filled conduit as magma moves through it. On Earth, harmonic tremor recorded near a volcanic vent is one of the most reliable precursors to eruption. On Io, harmonic tremor is background noise. It is always present somewhere beneath your feet. You stand on the margin of the most persistent lava lake in the solar system, and you wait for the thermal wave to approach. The data your suit is recording will, in this story, eventually reach the same archives as Galileo's tape-recorded observations and Juno's GRUM scans. It will be one more measurement in a dataset that has been accumulating since 1979. The wave continues its approach, and you are still on the margin of Loki Patera, but the story is beginning to slow down now. The sentences will come more gently. The information will arrive in smaller pieces. There is no less to know. The universe does not run out of things to say about a world like this, but the body is asking for rest, and the mind, given the right conditions, will follow. So let the pace change. Let the numbers recede for a moment, and let what they describe remain. Io is approximately 3,643 kilometers in diameter, almost exactly the same as Earth's moon. If you placed Io next to the moon in the same sky, at the same distance, they would appear indistinguishable in size. Two moons, nearly identical in diameter, built from roughly similar starting materials, silicate rock and metal, and yet almost nothing else about them is the same. Earth's moon is geologically dead. Its last significant volcanic activity ended approximately 1 billion years ago. Its surface is preserved from that era, ancient, cratered, cold, unchanged at the scale of human observation. Its interior has cooled to the point where the heat still escaping from it is too low to drive any active geological process. The moon is what a world looks like when its energy source runs out. Io is what a world looks like when the energy source cannot run out. The difference is not composition, it is not size, it is orbital position. It is the fact that Io formed where it formed, close enough to Jupiter and in resonance with the right neighbors, that the gravitational system it is embedded in will not allow it to cool. Two moons, one orbit, one dead, one burning. The crust beneath you on Loki Patera's margin is approximately 30 meters thick at this location. 30 meters of solidified silicate rock between your feet and liquid magma. The temperature at the base of that 30-meter layer is above the melting point of basalt, approximately 1,100 degrees Celsius. The temperature at the surface where you stand is 300 degrees. The gradient across 30 meters is 800 degrees. On Earth, the geothermal gradient in most continental regions is approximately 25 to 30 degrees Celsius per kilometer. Here it is more than 25,000 degrees per kilometer. The heat is not patient. It moves through rock by conduction, by the slow transfer of thermal energy from atom to atom, and at these gradients, it moves quickly. The surface of this crust is radiating energy upward into the thin atmosphere above it at a rate that, if it were occurring across the entire surface of Earth, would be detectable from interstellar distances. But it is not occurring across the entire surface of Earth. It is occurring here on 200 square kilometers of frozen lava lake, on a moon 628 million kilometers from Earth. And it has been occurring without interruption for longer than complex life has existed on Earth. The timeline is worth holding quietly. Io formed approximately 4.5 billion years ago, along with the rest of the Jovian system, from the disk of material that surrounded the young Jupiter, as the solar system itself was still condensing. The Laplace resonance that drives Io's tidal heating established itself within the first few 100 million years of the solar system's history, as the orbits of the inner Galilean moons evolved and settled into their current ratio. Life on Earth, multicellular complex life, is approximately 600 million years old. The first animals in the fossil record appear around 540 million years ago. Modern humans, Homo sapiens, have existed for approximately 300,000 years. Io has been erupting since before complex life on Earth existed. It was erupting when the first fish developed jaws. It was erupting when the first plants colonized land. It was erupting when the dinosaurs appeared, persisted for 165 million years, and disappeared. It was erupting when our ancestors first used stone tools, when the first writing was invented, when a man in Padua lifted a telescope to his eye on a January night in 1610 and noticed something small and bright near Jupiter. The volcanic activity that Voyager 1 discovered in 1979 was not new. It was not a recent development. It was the current expression of a process that had been running since the beginning. The thermal wave at Loki Patera reaches your position. You feel it before you see it, not as heat through your suit, which is managing the temperature, but as a change in the sound that isn't sound, a low vibration through the soles of your boots as the crust ahead of you begins to fracture under the weight of the foundering process. A crack appears in the polygon surface 3 meters ahead. Then another. The cracks widen slowly, not suddenly, revealing an orange-bright line of exposed magma below, too narrow to see into, but bright enough to register as a glow against the fractured dark gray crust surface. The foundering has reached your position. You step back 1 step, 2 steps, onto older crust behind you. The process continues ahead, methodical, indifferent, physical. The crust breaks along its polygon boundaries, sections tilting as one edge sinks faster than the other, fresh lava welling up through the gaps and spreading in thin sheets across the sinking surface before it too begins to cool and solidify into a new layer that will itself eventually founder in a future pass of the thermal wave. The cycle is visible in real time. The timescale is not geological here, it is observable. You are watching a world rebuild its own surface in front of you, 1 square meter at a time, at a rate that your eyes can follow. You step back again. The new lava surface behind the advancing wave is bright for a few minutes. Then it dims as the top layer cools. Then it darkens to a deep red, then to a brownish gray, then to nearly the same dark gray as the older crust around it. The cooling happens fast in the low-pressure environment. There is no atmospheric gas to insulate the surface, no convective heat transfer to slow the radiation of energy upward. The surface cools by radiation alone, and at these pressures, that is efficient. Within an hour of being exposed, the new surface is cool enough to walk on. Within a day, it is indistinguishable from crust that has been there for weeks. The lake is rebuilding itself behind the wave, meter by meter as the wave advances ahead. You watch until the advance has moved far enough that the immediate crust under your feet is stable again. Then you stand still. You let the scene exist without adding more to it. Above you, Jupiter fills its quadrant of the black sky. Its bands are slightly different from what they were 6 months ago. Jupiter's atmosphere is not static, and the cloud patterns shift across the planet's face on timescales of weeks to months. The Great Red Spot has been shrinking over the past century of observation. When first measured in detail in the late 1800s, it was estimated at 40,000 kilometers in diameter. By the early 21st century, it had decreased to approximately 16,000 kilometers. The storm is still there, still rotating, still larger than the diameter of Earth, but smaller than it was. Even Jupiter's oldest storm is changing. The sun moves toward the horizon behind you, not because Jupiter has moved, but because Io is rotating on its axis once per orbit, once per 1.769 Earth days, and the sun is completing its slow arc across the sky. You have been standing here for a significant fraction of an Ionian day. The sun is low now, the shadows long, the sulfur dioxide frost on the surrounding plains catching the low-angle light and glowing a deep amber rather than the pale yellow it shows at high sun angles. In the long shadows, the topography of Io's surface is more visible than it is under overhead illumination. The low ridges of the compressional terrain to the south stand out clearly. The subtle undulations of the sulfur plain to the north are visible as a series of gentle waves, each wave perhaps 2 or 3 meters high, extending to the horizon. These waves are not wind-formed. There is no wind. They are the surface expression of successive lava flow margins, each flow slightly thicker than the last, each one buried under the next, the edges creating low steps that are smoothed by subsequent sulfur dioxide deposition into gentle rolls rather than sharp scarps. The landscape is a record. Every feature in it is a consequence of the same process you just watched in miniature at Loki Patera's edge. The same foundering, the same overturning, the same cycle of eruption and cooling and burial, expressed at every scale from the meter-sized polygon cracks in front of you to the kilometer-scale flow margins visible on the horizon. You breathe? Not literally, the suit manages that, but the narrative grants you a breath, a pause in the accumulation of information, a moment in which the scene exists without explanation. Jupiter in the sky, the glowing line of Loki Patera's active front, now several hundred meters away and receding. The frost plains silent in the amber light. The mountains to the south, their peaks catching the last of the direct sunlight, the scarp faces already in shadow. Io is quiet right now, in the way that Io is ever quiet, which means the major eruptive activity is distant enough not to be directly visible from this position, and the background processes are too gradual to produce visible change from moment to moment. But you know it is not quiet. The seismometer in your suit is still recording harmonic tremor. The plasma torus overhead is still receiving its steady supply of volcanic material. Pele is still erupting. On the other hemisphere, its plume climbing 300 kilometers into the sky on the other side of this world. Prometheus is still advancing its flow front to the northwest. Loki Patera's thermal wave is still propagating, the section that just passed your position now well to your east, the section still approaching from the west some weeks away. The whole world is in motion. You are standing in the middle of it, and for this moment, the motion is slow enough to simply be present with. Europa is also in the sky, if you know where to look, a small point of light, distinct from the background stars by its movement relative to them over the course of an Ionian day. Europa orbits Jupiter at 671,100 kilometers from the planet's center, 250,000 kilometers farther out than Io. It completes 2 orbits for every 4 of yours. Right now, it is visible as a pale yellowish white point against the black, moving perceptibly against the star field over the course of hours. Beneath Europa's surface, beneath approximately 15 to 25 kilometers of water ice, the same Laplace resonance that is melting Io's interior is maintaining a liquid water ocean. The tidal heating at Europa is lower than at Io, the eccentricity is smaller, the distance from Jupiter is greater, but it is enough to keep the ocean liquid. That ocean, based on estimates from Galileo's magnetic field measurements and gravity data, is approximately 100 kilometers deep. It contains more liquid water than all of Earth's oceans combined. The energy that is incinerating Io is 250,000 kilometers away, keeping water liquid in the dark beneath Europa's ice. One source, 2 outcomes: fire and water, maintained by the same gravitational system, separated by distance and degree. Both are real, both are out there right now as you listen. Ganymede is also visible from here, a brighter point than Europa, moving more slowly because its orbit is larger and its orbital period longer. Ganymede completed 1 orbit in the time you have been standing here watching Loki Patera's thermal wave advance. Its surface, at 5,268 kilometers in diameter, is larger than the planet Mercury's. Its interior shows evidence of past tidal heating, a differentiated structure with an iron core, a subsurface ocean of its own, and a thin magnetic field generated by its own interior. But the heating has diminished as the resonance has evolved, and its surface is older and more heavily cratered than Europa's. 3 moons in the same sky, 3 different geological ages, 3 different expressions of the same orbital resonance. The sun reaches the horizon. Io's terminator, the shadow boundary, sweeps across the landscape as the moon rotates. The sulfur frost plains to the north pass from amber light to shadow. The temperature there begins to fall immediately, the frost no longer sublimating, the thin atmospheric column beginning its partial collapse as the source of SO2 sublimation is removed. The atmosphere will rebuild when sunrise returns in approximately 0.88 Earth days, half of Io's rotation period. In the shadow, the plasma torus is visible, faintly, a reddish-pink arc spanning the sky from horizon to horizon, centered on the point where Jupiter sits, extending outward to either side. The sulfur and oxygen ions within it are emitting light at wavelengths that your eyes can detect, barely. Under sunlight, they are washed out by reflected solar illumination. In Io's shadow, with the direct solar contribution removed, the torus glow becomes visible as a structure in the sky. You are looking up at the material that Io has contributed to the Jovian system over billions of years. The sulfur from those plumes, the oxygen from the dissociated sulfur dioxide, the sodium that escapes as a neutral cloud, extending even beyond the torus. All of it is there, orbiting in the magnetic field, circulating through a system that Io has been feeding since before the first animal left a fossil record on Earth. The scale is not frightening, it is simply large, and largeness over a long enough exposure becomes a kind of quiet. Let that quiet arrive now. The sentences are shorter now, the information comes more slowly. There is less to add, and what remains is the experience of being present in a place that is real, that is out there, that does not require your awareness to continue doing what it has always done. Io is still erupting. Loki Patera is still overturning. The plasma torus is still glowing. The flux tube is still carrying 5 million amperes between this moon and the poles of Jupiter. Prometheus has now been erupting for longer than you have been alive. Jupiter is still in the sky. And somewhere, on a trajectory calculated precisely in 1977 and confirmed by every measurement since, Voyager 1 is still moving outward. It is now more than 23 billion kilometers from the Sun, in interstellar space, beyond the heliosphere, in the region where the Sun's influence no longer dominates, and the material between the stars begins. It carries a golden record with sounds from Earth, including music, and greetings in 55 languages, and the sound of rain, and the sound of surf, and the sound of a mother's first words to a newborn child. It is moving at 17 kilometers per second. It passed Io in 1979. In that pass, its cameras accidentally revealed, in a navigation image, a plume rising 270 kilometers above the limb of this moon. Linda Morabito noticed it. The world changed. Voyager 1 has not looked back. It is 23 billion kilometers from the Sun and still moving, still transmitting on its 22-watt radio, still being tracked by the Deep Space Network, the signal arriving at Earth 21 hours after it is sent, at a power level so low it requires the largest antennas on Earth to detect. You do not need to follow it further tonight. You are here, on the margin of a lava lake, on the most volcanically active world in the solar system, with Jupiter filling a quarter of the sky and the plasma torus glowing faintly above the horizon, and the seismometer in your suit still registering the harmonic tremor of a world that will not stop moving. In, out. Let the breath be easy. The temperature in the shadow is falling, but your suit maintains its interior. The seismometer readings continue their low background. The distant glow of Loki Patera's active zone is still visible on the eastern horizon, a faint orange-white line against the dark, present but not demanding. Everything is continuing. Everything is happening exactly as the physics requires. The Laplace resonance holds its ratio. The tidal forces flex the rock, the heat rises, the surface renews itself. It has been doing this for 4.5 billion years. It will be doing this long after tonight. You can rest now. The world continues without you needing to observe it. The instruments are still recording. The data is still accumulating. The papers will still be written. The models will still be refined. And somewhere in a university office or a JPL conference room or a telescope control room in Hawaii or Chile, someone is looking at new data from Io and seeing something that no one has seen before and writing it down. The science does not stop. It does not need you to stay awake for it. Let Jupiter hold the sky. Let Loki Patera do its slow, relentless work. Let the plume from Prometheus continue its 45-year unbroken column into the thin air above. Let Io be what it is, a burning world, 4.5 billion years into an uninterrupted eruption, heated by a gravitational resonance that will not release it, painting its own surface in sulfur and lava and frost, night after night, orbit after orbit, with no audience and no pause. It is enough to know it is out there. You have been here long enough. You have seen what this world is. Now rest. If this story found you tonight, if this particular corner of the solar system was the right place to spend these hours, then a like or a subscription to Quiet Science at Bedtime means more than you might imagine. It is what allows these journeys to continue. Everything you heard tonight is real. Io is out there right now. Good night.